Yeah, so let's get started. Just to recap, we finished reinforcement learning, and now we're moving on to this part of the course that we're calling Monte Carlo planning, and it's all about using a simulator to make decisions. And the model you want to have in mind is you've got your agent robot here acting in the real world, and the robot also has a simulator in its head that basically it can think about acting in the real world at a much higher rate than acting in the real world. And so the question is, how do you actually use that simulator to make good action choices? And we talked about the relationship between reinforcement learning traditionally and this Monte Carlo planning. And so what was the main difference between what we're calling Monte Carlo planning, that framework, and reinforcement learning? Anybody remember this?
So multicolor planning has a strong simulator where you can reset the state to any state. But in reinforcement learning, not so much. We may be only able to set a state to certain initial states.
Right. So reinforcement learning, you're kind of stuck in the world, right? You're still learning from these experiences that you sample, but you're stuck in the world. And Monte Carlo planning, you can sample experience wherever you want. And so it's a pretty big difference. And as I said last time, I'll repeat again. When you see a lot of reinforcement learning work being done is, it's done in this sort of fictitious way where we're pretending we're in the real world, but we're not. And we rarely ever do reinforcement learning in the real world. And so knowing these other methods, I think, is pretty important. We saw one example already where they were training an Atari policy on sort of supervised data produced by Monte Carlo tree search, which uses Monte Carlo as a form of Monte Carlo planning. And that turned out to work better than, at that time, the reinforcement learning algorithm that treated the simulator like it's in the real world. So, and it took millions and millions of simulations. So that's where we're headed. Then we did this strange thing where we said that we're going to focus on Monte Carlo planning for the case when we just have a single state, which seems kind of silly. So solving a single state MDP, if you know the model, is pretty trivial, right? You just take the action with the highest reward. But if we only have a simulator, maybe there's still something to solve there. There are some simple mechanisms to try to do this, but we're going to look at the mathematics of this, and it also corresponds to this multi-arm bandit problem that I talked about last time, which is a traditional problem originating in statistics that has some interesting stories behind it, and also we're going to use it as a component of bigger Monte Carlo planning algorithms. So that's why we're doing this. And so just to review, this is our multi-arm bandit problem. So we can think of it as having a single state, but the state is not terribly important if there's just a single state. Really what we have is a bunch of options in front of us, and the options are what you call bandits. They might call these arms, and these are slot machines from Vegas. And every time you take this action or choose this option, you pull the slot machine arm, and it gives you a random outcome. And the outcome is a number, and generally you want to get high numbers, right? You want to get a lot of money from these machines. So that's a setup, and in our framework, these R functions these are randomized reward functions, remember. And whenever we pull an arm, we would call this function, right? Remember, in the Monte Carlo planning setup, we're always thinking of we have these basic functions, like a function to simulate the state and a function to return the reward. We're building algorithms out of those functions. And here, all we need to do is have the reward function because which could be implemented in any way that you want. But since there's only one state, the transition model is unimportant. All right, and these arise in many situations, and we talked about clinical trials last time and how maybe if we are interested in finding the best best treatment for a disease, maybe there's better ways to do it than having equal numbers of people in placebo and your treatment. And these sorts of, so if you were to not have equal numbers and do a trial where you're adaptively figuring out, do I want to put this new person in placebo or treatment? That would be an adaptive type of experimental design, which is a little controversial in circles, but it's getting more and more popular, and I think that's probably how things will go eventually. Now that we have, now that we're in the era of big data and collecting lots of digital data, it'll seem unethical almost to do some of these placebo trials. So the other area is online advertising, and this is a place where a lot of your peers and a lot of really smart people are working, right? So if you go to, lots of companies have been formed around selling people, being able to get people to click on your ad, right? So lots of money to be made there. And it can be formulated as a bandit problem, and often is. And so you'll see a lot of people at the industrial labs working on different forms of bandit problems, because it often arises from advertising. So here, you imagine you have different ways of showing ads, right? Maybe you have 3 different ways. You're going to flash something in front of them, and then something else, and then something else. And you want to know which of these is going to be most effective. And so the arms are going to correspond to the different types of ads that you could show. And the trials are, and when you pull an arm, it's basically you've got a user and you show them an ad, right? And then you get to see if they clicked on it or not. Right? That's your feedback. And you're trying to maximize the number of clicks you get, the click-through rate. And so this is a pretty straightforward formulation. And there's lots of extensions to this. So you'll hear people talk about contextual bandits, which is a version of multi-arm bandits where maybe the right arm for her is different from the right arm for him, right? And so contextual bandits, you get to see, the simplest cases, you get to see a feature vector about the situation, and then you get to choose an arm then. So contextual bandits will have a form of generalization, whereas the basic bandit setting there's no state about the current situation. So contextual bandits are almost like, there are multiple states which correspond to sort of the multiple people in advertising, but the planning horizon is just a horizon of one. Right? That's how you want to think of it. You pull an arm, you get a reward, and then you get the next person, you pull an arm, and you get a reward. So it's similar to sort of supervised learning, but it's a little bit different. Right? Because in supervised learning, if I give you an example, I will show you I'll show you the right answer, right? So supervised learning, I'll give you an example of any of you, and I would show you what arm is best, and you would learn to try to predict that arm. In bandits, you don't get such information. You have to actually try the arm, and you get to see the result for that one arm. You don't get to see the result for the other arms. So it's a little bit different, but it's sort of in between. It's sort of the middle ground between reinforcement learning and sort of traditional supervised learning. So this is an area, but I hope that you won't. I hope most of you won't work in this area because so there's a lot of people that are very proud at how easy it is to get people hooked on things, right? And there's a lot of people spending lots of energy and money and time optimizing the degree that we can get people hooked on things, including kids, right? So I have kids, and I see the ads that they try to send these kids, and it's at some level it's very distasteful, but this is going to be an option for you, definitely. And so I would say definitely think about the job that you take, and do you want to spend your life optimizing distractions for the human race, right? Because people are extremely distractible, and it's not anything new that people are easily manipulated. And now we can do it even better with algorithms. And so let's think about that. Or would you rather do something else, right? So, but it is a great way to make money, that's for sure. All right, so now we'll get into the actual material, and we're going to make a couple of assumptions to actually talk about this mathematically, and the assumptions we're going to make are about bounded rewards. There are different ways that you could formulate this, but we're going to assume that the slot machines have bounded rewards, and or our arms have bounded rewards between negative R max and R max. And since we have random reward functions, this is what it means. Right? The probability that the reward you get is between these ranges is 1. There are cases where you'll study bandit problems where there's not a bound. Like if sometimes people study Gaussian bandits, where every arm corresponds to a Gaussian distribution with a mean and a variance, and you're trying to figure out how to maximize your return. There's no bound there on the range, right? Gaussians have infinite extent, but you use some slightly different analysis techniques there. But for something like a Gaussian that doesn't have a heavy tail, these things will work pretty well anyway. If you just you can find a point where essentially the probability of getting something beyond R max and negative R max is minimal. But there are different analyses, and you can always look those up if you need them. But for now, we'll deal with the bounded case. And remember, I said when I give you a bandit problem. So what a bandit problem is going to be a bunch of arms, right? So we give you some arms, and you can pull them, right? And you can see the rewards, but you have to know what the objective is. Like, what is your objective? And an algorithm is going to try to optimize some objective by pulling arms in some sequence, right? So a bandit algorithm is nothing more than something that looks at the history of its arm pulls and selects the next arm to pull. And as I said last time, we're going to study 3 different objectives and talk about algorithms that try to achieve those objectives. And the first objective that we're going to talk about is something called probably approximately correct. This bandit objective. Now, who's ever heard of PAC, or probably approximately correct, right? So this is a term that this type of analysis is often done in computer science. It's not anytime you have randomized algorithms, you'll often see analyses that deal with probably approximately correct. It's also in learning theory, machine learning theory, is a very famous concept as well. So sort of orthogonal to this class, it's good for you to see this term and get to see what it means, right? So there's going to be, whenever you think of probably approximately correct, what should come to mind after you know this is there's going to be an epsilon and a delta. And you want to be very clear about what epsilon and delta mean. And so hopefully by the end of this lecture, that'll be clear. But it sounds like a pretty unmathematical thing, like probably, approximately. It's like somebody's trying to weasel their way out of being accurate somehow. But it actually, the probably and the approximately actually have very precise meanings and uses, and we'll see that. But basically what this means, what we're going to try to do is we're going to try to, we want our bandit algorithm, in this case, we want it to eventually pull arms and stop at some point. And when it stops, it's going to tell us the index of an arm. And we want that arm to be probably, approximately the best arm. Right? So approximately means it's close to the best arm. And probably means that with high probability, it's the best arm, right? And so that's what we're going to be studying here. So we want our algorithm. We're going to tell it this is this is the probably I want you to achieve, and this is the approximately I want you to achieve. And it will pull the arm some number of times and output an arm, and it has to meet the guarantees that we want it to meet. So let's dig into the probably and the approximately and see what their purpose is. So what about the probably? So this is an example. So we've got a bandit problem, and there's just two arms. And this arm here, you get a reward of 1 with probability 0.001. Okay? And you get a reward of 0 with probability 0.999. So most of the time, 1 in 1,000 times, you're going to get 0. You're going to get 1, but most of the time, you're going to get 0. So it doesn't look like a very good arm to pull, right? You're going to has an expected value of 0.001. Whereas this arm, has an expected value close to 1, right? Because you get a reward of 1 with 0.999, and otherwise you get a reward of 0. Right? So which is the best arm? A2, right? That's obvious. Now, do you think it would be easy to determine which the best arm is by pulling these a few times? You think it would be? What would you do? This is not complicated.
Just randomly try and
Pull each one some number of times, and yeah, most likely you would find the best arm, right? If you pull them each 10 times, you would probably correctly identify the best arm. But so let's go to the extreme. So suppose we're going to try to determine the best arm by pulling each one 1,000,000 times. Okay, so that should almost surely, well, I shouldn't say almost surely, should with high probability return only the statistics people got that, but or maybe some others, but almost surely means with probability 1. So we're not going to guarantee that. In fact, that's the whole point of this. So if we pull these 1,000,000 times each, will we always identify the best arm? Like, can we guarantee with probability 1 that we'll always find the best arm? She says no. What do people think? Is everybody saying no? Everybody's saying no, maybe. So why not? Why might we not find the best arm if we pull them each 1,000,000 times? Ideas? Yeah.
The probability of making a mistake is very tiny, but it's not 0.
Mm-hmm.
There's still, it's like as you pull the arms more often, the probability of making a mistake increases, but still it's not 0.
Mm-hmm. Right. Because we could pull this arm 1,000,000 times, and there's a non-zero probability that every time we get a 1. Right? It's tiny. It's like 0.001 to the 1,000,000th power, but it's not 0. And likewise, we could pull this arm 1,000,000 times, and we could get 0 every time. And so vanishingly unlikely, but still, you can't say probability 1. So you can't say always. You can't guarantee that this will always work in theory. So this is why we have to, like in theory, have a probably in all of the results. You can say we can identify the best arm with high probability, but we can't guarantee that we can identify the best arm because you may just get unlucky. And so this is really a theoretical point, but a very important one. And that's why we have the probably here. And a lot of situations in computer science will have this sort of thing come up, and statistics. So there's a whole area of randomized algorithms, and almost always you're going to have a probably in those analyses. All right, so I think I just said this. All right, so now how about the approximately? Here's an example that kind of illustrates why we need to talk about approximately. So here's an arm where there's sort of equal probability of seeing a 1 and a 0. right? So the expected value is going to be 0.5. And here's an arm where, well, it's very close to being equally probable for, so arm 2 equally probable for a 0 and a 1, but not quite equal. It's a little higher probability for observing a 0. Right? So now what we want to think about is, suppose you're trying to determine which arm is best. Like you want to know which arm is absolutely best. So which arm is absolutely best here? 1 or 2? 1, right? Because it has a slightly higher expected value. The expected value here is 0.5. The expected value here is 0.499999, right? So to get a procedure that's going to determine which is the best arm, are you going to need, is it going to be hard to do that? Are you going to need a lot of poles or a small number of poles, do you think? Yeah. If I put these two machines in front of you and I said, don't go away until you can really be sure which one is best, are you going to be here a long time pulling arms, right? Compared to our previous one, right? It's going to be a long time because this is a very small difference, and the statistical noise is going to dominate that difference for a very long time, right? So in order to have any sense that you're returning the absolute best arm, you're going to have a ton of poles to handle these types of cases. Like these are the really hard cases, but in theory, you have to handle them. And so in order to, in theory, have to be able to bound the number of poles to a reasonable level, we're going to talk about returning the approximately best arm. Because in practice, in most applications, you would not care about this difference. You're like, okay, yeah, so what? They're very, very close. I would be happy to have either one. There might be some other arms that are much worse or much better, and we want to choose correctly there. But if these are the two best options and everything else is much worse, we'd be happy to return either one of those in most situations. In some situations, maybe not. And in that situation, you're going to have to be ready to do a lot of arm pulling, right? So this is so here. This is why we introduced the approximately. If we only care about returning approximately the best arm, we can sort of do a little bit better, because most likely our approximately bound, like how close we want to be to optimal, will be within this limit, for example. Right? So any questions about probably and approximately? Right? So these have very specific meanings. They're not these sort of fuzzy terms that it sounds like when you first hear about probably, approximately correct. So, if you told me that on an exam, my answer is probably approximately correct, I'd be like, I don't know, that's just wrong. But here it means something. Okay. So now let's look at some algorithms. So we've kind of done the informal definition of PAC, but now we actually need to do the formal definition, and it's kind of a pain to look at. But I don't know any other way to do it. So in this, we're going to say the number of arms is K, and the max reward is R star. Okay, so our goal is to, at the end of the day, our algorithm is supposed to return the index of the arm that achieves R star or something close to R star, right? If we could choose, this would be the argmax of this is what we would want to return. And we're assuming we have these bounds on the reward. So now, this is the definition that we need to look at for a while. And this, as I said, it looks pretty intimidating, but it's actually fairly simple once you parse the basic pieces. Okay, so first of all, let's make sure we understand what a bandit algorithm is. I've said this before, but we'll say it now again. So we're going to call the ALG, this is our bandit algorithm. Okay, And the bandit algorithm is nothing other than something that will pull a sequence of arms. It gets to see the result of each arm. And at some point, our algorithm here is going to stop after it's pulled a sequence of arms. And it also has to determine how many pulls to do. It's going to stop and return an index, okay, of an arm. And it's basically telling us this is what I think is best, or approximately best. Right? So that's what the algorithm is going to do, the bandit algorithm. And this definition is about when we can say a bandit algorithm is PAC. When is it an efficient PAC algorithm? Okay? And so let's look at this a little bit. So our algorithm is an efficient PAC bandit algorithm if and only if all of these things are true. So it has to satisfy something for any multi-arm bandit problem you give it. Right? So the two that I showed you, those extreme cases, it has to work for those. It also has to work for any other bandit problems. Okay? Our algorithm is going to get two inputs, delta and epsilon. And after you've seen PAC and understood it, whenever you hear PAC, you're going to be thinking, oh yeah, there's a delta and an epsilon. Right? Delta is going to be our probably, and epsilon is going to be our approximately. So delta and epsilon are given to the algorithm. And algorithm then has to pull a number of arms. So it gets it's going to do some arm pulling. And we want that to be polynomial, this is the efficient part, in 1 over epsilon, 1 over delta, R max, and K, and then return an index such that with at least probability 1 minus delta, the index is close, the reward of the index is close to the optimal. Okay, so it's epsilon close. So let's think about this again. So our algorithm is going to pull arms a number of times. Eventually it will stop, return an index j. Okay? And what the algorithm has to guarantee is that with probability 1 minus delta, that arm has a reward that's approximately correct, approximately optimal, and in particular within epsilon of optimal. Okay? So what we say about this thing being efficient is that the number of arm pulls that it can do is polynomial in 1 over epsilon and 1 over delta. So let's first think about why that basically means the number of arm pulls will increase as delta gets small and epsilon gets small, right? So why does that make sense? Why would we expect in order to meet our guarantee, the algorithm is going to have to do more pulling for small epsilon and small delta? Does that make sense? Make sense to somebody? Make sense to anybody over here? Right. So if I say I want you to guarantee that with probability 0.99999, you give me an approximately good arm, compared to I want you to guarantee with probability 0.5 that you give me an approximately good arm. It's much harder to get the 0.999, and that means you're going to have to do a lot more arm pulling to be sure that you're going to return something within that guarantee. Right? And similarly, if I say I want you to return something that's within 0.0001 of optimal, you're going to have to do a lot more arm pulling compared to I want you to return something that's within 0.5 of optimal. Right? That's not nearly as hard. So this kind of makes sense, and this is what you'll generally see when these algorithms when we're talking about PAC. You're allowed to do more work for smaller epsilons and smaller deltas, because when those get small, it's sort of like asking more out of the algorithm. The guarantees are tighter. And well, if there's more arms, K, well, of course, you're going to have to do more arm pulling, right? You would expect that to be something like linear in K or something. And R max, yeah, when there's a larger maximum reward, Why might we have to do more arm pulling then? Any ideas? To achieve a guarantee, yes.
I think it's similar than when you talked about RMAX last time. It's like if you have a teeny tiny probability of this RMAX, if RMAX is very small, we may not worth to pull more arms to get to it. But if it's very big, though the probability is very small, we still want it.
Right. Yeah. So to paraphrase, basically so you can have so in theory here you have to handle all the cases. That's why these things are a little difficult. You're going to handle all the cases, including a case where you have an arm that basically it's always zero. It always returns zero, except a small probability it returns a very huge number. It's like a slot machine that has a huge payout very, very rarely, right? And if that huge number is large enough, that's going to be a really good arm in expectation. But in order to identify that, you're going to have to pull it a lot of times to get that big payout, right? So, of course, in Vegas, the big payouts are not going to be they're going to be, it'll be a small enough probability so that overall Vegas will win. Here we're thinking you might be able to, there are bandit problems where you can win. But that's why the bigger our max is, the more tiny events could influence the expectation. All right, so I don't know, any questions about this definition? Yes.
Would it help if we also try to model the probabilities of getting the rewards?
So you could, so we haven't talked about algorithms yet. You could try to estimate some distribution of the rewards. The algorithms that we're going to talk about are all sort of assumption free, so they don't assume anything about the distributions other than a bounded support. Generally, if you assume something about the distributions, you can get better results, but that's because you've assumed something about the model. So they'll have if you have Gaussian distributions and you assume that, then you can do better than if you assume just a general bounded support distribution. Yeah. All right. So any other questions? All right. So now, what we want to do is figure out how to get a pack algorithm, right? And so, so what's the simplest bandit algorithm possible? Right? If I were to, if I were to go up to a kindergartner and ask them to figure out what's the best algorithm to find the best arm. I'm going to give you a budget of arm pulls. What would you do? Maybe not the best, but what's an algorithm?
Divide the budget for each arm.
Yeah. So you just pull each arm an equal number of times. You would see which arm has the best average reward, and you would return that arm, right? So that's pretty simple. And that's actually, so this is a paper that talks about pack bounds for multi-arm bandit problems, and MDPs, but the multi-arm bandit is really the biggest thing here. And the most basic algorithm, this is sort of the starting point, is this uniform bandit algorithm. Pull each arm W times and return the arm with the best average reward. Right? So this is a completely unsurprising algorithm, not very interesting. But what do we have to do in order to make this into a pack algorithm? Right? So our bandit algorithm has to decide when to stop. Right? So our bandit algorithm has to decide the value of W here. Right? And so all that's left to define the algorithm is to define how does the algorithm choose the value of W. Right? And you have to choose the value of W to be large enough so that you meet the guarantees required by the pack definition. Right? So all we're going to be doing here is trying to figure out how big W needs to be. And this is going to be very similar. We're going to use the turnoff bound again. Very similar to when we talked about estimating the statistics of an MDP in finite with finite samples. All right. So can we make it efficient? So we've been over the Chernoff bound before, so we'll just quickly review this. But so if you remember, the Chernoff bound was we have a random variable r, and here in this context, you can think of that as being corresponding to one of the arms, right? And we can sample that random variable, and get ri, is one sample. That's like pulling an arm, and you get a number for that. And then we were interested in bounding the probability that the average of those numbers is far away from the expected value, right? So this is like the true expected value of an arm. This is the average of W pulls of the arm. And we want to bound the probability that that difference is greater than epsilon. And the Chernoff bound said that that difference sort of decreases exponentially with W, the number of pulls. Right? So as you pull the arm more and more, the probability that you're going to sort of have an error, an epsilon error, goes down very quickly. Right? And so this is exactly what we saw before. We're just kind of reviewing it. And the other way of writing this, which is often the more useful way of writing it for your application, is equivalent to saying with probability at least 1 minus delta, we have that our error is less than this quantity here, right? And so again, as delta gets smaller and smaller, this gets larger and larger, right? And that's what we would expect. As W gets larger and larger, we expect this to go down, and it does. It's the square root of 1 over W. So that's the Chernoff bound. That's what we've seen before. Any questions about this before we move on? All right. So we saw the coin flip example before. So now we want to apply that here, right? And the basic idea is, well, you could apply the Chernoff bound to each arm independently, right? And then somehow we have to sort of combine all those results together. So let's do that. So this is just kind of a simple application of the Chernoff bound. So we're going to consider a single bandit arm, right? And for a single bandit arm, we've pulled it W times, right? And we have the samples from that arm. And so this, if we just use a Chernoff bound, I'm going to use delta prime here. We'll see why for a second. But delta prime is going to be our sort of probability guarantee for a single arm, right? And basically, this is all we have. So we can bound the error by epsilon. If we sort of set this equal to epsilon, we say that W, if W is greater than this amount, then we're going to guarantee with 1 minus delta prime probability that our average is within epsilon of the expected value. Okay? So this gives you sort of a bound on how much you need to pull a single arm to get a guarantee, a pat guarantee for a single arm. Okay? So is that fine? And you can see this has all the properties that we'd like in some sense. So W, like the number of pulls for a single arm here is, well, it's polynomial in 1 over epsilon, right? It's 1 over epsilon squared. And it's polynomial in delta prime, 1 over delta prime. Actually, it's logarithmic in 1 over delta prime. And this is usually what you'll find. The probably parameter, it's much less costly to make that small because it's usually in a logarithm somewhere. So now that's how you do a single arm. But now let's say the three of you are arms that I'm going to pull, and I can guarantee with delta prime probability that or 1 minus delta prime probability that you are going to be a good estimate, and that you're going to be a good estimate, and that you're going to be a good estimate, independently. Like you each have a delta prime probability of, and what this means is you have a delta prime probability of making an error. And so let's say let's say it's 0.1. Okay, so he has a probability of making an error. She has a probability of making an error of 0.1, and she has a probability of making an error of 0.1. Now, is it the case that if I were interested in them all being correct, that the probability of one of them making an error is 0.1 or less? Or is it higher? Yeah, at least one of them making an error.
Are they friends? They're independent.
Oh, they're independent, yeah.
Okay. Then this 1 minus 0.1 square. I mean, not cube.
Yeah, so we could figure it out exactly if we wanted to. But the point is, they each have an independent chance of making an error, and that chance is 0.1. And so, as a group, it's more likely that one of them is gonna make an error. It's more likely than 0.1, right? So basically, we have to, and if we're doing multi-arm bandits, we want all of them to be accurate. Like we want all of them to be accurate with 0.1 probability. And so what we need to do is we need each of them to have slightly better guarantees than our overall guarantee. So if I want them as a group to have a guarantee that none of them make an error with probability 1 minus delta, they need to have better than delta error probability. And what would you guess that needs to be? So if I want, as a group, to have an error rate no more than 0.1, what could each of their error rates be, do you think? 0.1, maybe divided by 3 or something. We could do this exactly, but it's a pain to work with exactly. So we're going to use something. We're going to use something like the very simple result called the union bound, right? So this is if for any events, right? So these are probabilistic events, k events, and here we have 3, right? And the events we're interested in are him making an error, her making an error, or her making an error, right? So A1, A2, A3 are, do they make an error? And the probability that one of them makes an error, A1 or A2 or A3, is less than the sum of the probabilities of each of them making an error. Okay? So what this says is that if each of them has an error probability of delta, then as a group, their error probability is going to be less than 3 delta. Does that make sense? This is just the union bound. And that means that they're going to be correct as a group with probability 1 minus 3 delta. So what we can do, and that's what we're saying here, right? So if we have k arms, and each arm is guaranteed to have an error rate lower than delta prime, then as a group, k delta prime is a guarantee on the error rate of the group, okay? And that means that if we pick delta prime to be delta over k, then all the arms are going to be epsilon accurate with probability 1 minus delta. All right? So all the stuff I'm doing here is just very cookbook type of analysis that you'll see applied over and over again. So this Chernoff bound, then the union bound, this is just like something that is a cookbook analysis after a while. And then we can use that to sort of get our final result. So if W is greater than or equal to this quantity, and notice here we, instead of having 1 over delta prime, we have 1 over, we set delta prime equal to delta over k, and so you get k over delta here. This is our main result. So if W is greater than this, then all the arms are going to be guaranteed to be within the epsilon bound with probability 1 minus delta. All right, and so that gives us a value of W that we can use and to get our guarantee. And I think we're just about done. So just to finish, now we can consider, well, what's the total number of simulator calls, right? The total number of calls to our simulator or the number of arm poles. That's going to be K, the number of arms, times W, right? And which, if we look at our previous slide and look at W, that's just, this is what we get, right? So you get a K log K, and then all this other stuff. And so if we look at this, we can look at the scaling. So it's, as I said, this delta parameter, that's always something you can make very small without much of an impact. The epsilon, on the other hand, that grows very quickly. 1 over epsilon grows pretty quickly as epsilon gets small, and then this is a square of that. So that's pretty impactful. And so when you see a result like this, so this is a PAC algorithm because it's all polynomial in these quantities. When you see a result like this, you have to ask, well, is it the best you can do, right? So this is a particular algorithm. We've given a particular bound. We've said, oh, there exists a PAC algorithm. That's what we've shown here. But is there a better PAC algorithm? Can you do better? And it turns out you can. And in fact, basically the way that we're going to be able to do better is we're going to be able to get rid of this log K. And we're going to do that with a fancier algorithm, which is also kind of interesting. And we'll talk about that next time.